modulus, P is the maximum stress. The function of Y in the strength equation can be understood when it is remembered that the stress P, thus the resistance, increases uniformly with the distance from the neutral axis, as Y increases in the formula for a given bending moment, and I divided by Y decreases uniformly. P will increase uniformly, therefore satisfying this requirement. This formula is based on the problem this formula is basic to the problem involving beam stresses and to the problem of structural strength of ships. The formula can be expressed and used in various ways. For example, if you're dealing with a beam of a given section modulus, SM, and want to know what the maximum bending moment on the beam can take with the proper factor of safety using equation 1, which we stated above, or you can propose to place a known external bending moment, or think of it as a loading, on a mild steam structural shape and know what the maximum stress permitted on the flanges of the shape with the proper factor of safety is around 7.5 tons per square inch. You may then divide the known bending moment by 7.5, and the proper section modulus is indicated by the following. Bending moment divided by the force equals I divided by Y, which is the section modulus. That's equation 2, shown on page 228. In a simple matter, then, to select a standard shape for a known section modulus at least equal to or than the required, or with a given bending moment and a given section modulus, you may find the resultant maximum stress as indicated. And this would be section 3. So if we know the bending moment divided by the section modulus, we know the maximum stress that the beam should be able to take. When a naval architect designs a ship to assume the maximum bending moment and knowing a strength of steel, the safer factory building can be calculated the required section modulus for the hull girder as shown in figure 2, or equation 2, which is the bending moment divided by the stress, the strength of material. Knowing the section modulus will give him a structural member in the ship where they are needed to produce the required resistance to bending and adequate longitudinal strength. Longitudinal strength of ships. When the foregoing outline of the theory of general field of the strength of material is in mind, a study of the strength of ships where this theory may be applied to an explicit problem of design may be undertaken. The study of the strength of a ship may be divided into two rather broad considerations. Local stresses. It is apparent that each individual member of the structure of a vessel be adequate to withstand the proper margin of safety of the stress due to such local loadings as hydrostatic pressure, concentrated weights of like a machinery, mass, propeller vibration, dynamic effects of liquid, special stresses encountered in dry docking and launching the vessel, and so on. The second is structural stresses on the complete hull girder. The problem here is to investigate the stresses which result from inequalities between the weight acting down and the buoyancy acting along the length of the ship. These inequalities create shearing and bending moments, both longitudinal and transverse on entire hull of a ship. Just as in a loaded beam must possess the resisting moment for bending potentially large enough to resist any of the reasonable bending moments, so must the ship possess reasonable resisting moments to bending in order to withstand the loads placed upon it. In this section, the longitudinal stresses acting on the hull of a ship will be studied, since the provision of material adequacy to resist longitudinal stresses will, in general, automatically provide for the transverse stresses. And now we're going to talk about beam theory of ship's strength. It is impossible to ascertain the necessary dimensions of a beam of this type and extent of the load to be placed upon it, the material of which it is made, and the fixity of the end connections are known. The same procedure is applied to ship designs in the problem of obtaining the necessary longitudinal scantlings of the ship's hull. Now, of course, the hull of a vessel moving through the seas is not directly analogous to the static load placed upon a beam in the structure of a building. However, the use of the beam theory, quote-unquote beam theory, of the ship's strength does not presume to produce an exact answer to the problem of obtaining bending moment produced on a vessel in a given condition of loading and a given wave condition. The results from this method are only approximate. The important thing to remember is that the calculations of strength for all vessels are made in a similar manner. The results may be accurately analyzed. Thus, if the scantlings of a vessel are arrived at by the beam theory and the failure occurs, the scantlings may be appropriately increased for future vessels. Although many years of experience, classification societies and others have found that the beam theory does produce satisfactory tentative basis on which the strength of vessels can be based. Application of beam theory to vessels. Calculations necessary for application of beam theories to vessels are listed as follows. 1. The maximum reasonable load which the hull of a vessel considered as a girder or beam will be called upon to assume this load will consist of three things: reasonable severe conditions of loading, a still water protected harbor condition, and C, a reasonable severe sea condition. 2. Bending moment and shear resulting from this maximum reasonable load are stresses computed by shear and bending moment diagrams. 3. The section modulus necessary to withstand the proper margin of safety, calculate the bending moment, and resulting tensile and compressive stresses of the upper and lower flanges of the hull girder. Consider first what the ship designer considers a reasonable severe condition of loading. If a vessel is loaded in such a way that all possible dead weight was loaded at a midship section of the vessel, it is apparent that it at a very severe bending condition would be induced. The vessel would tend to sag. On the other hand, if all the dead weight were loaded at the end compartments, the vessel would tend to hog. See Figure 10-6 on page 231 for examples of hogging and sagging for this narrative. However, the suppositions are for unreasonable severe loading conditions. The designer does not build enough strength into the ship's hull to assume such stresses. What then are reasonably severe conditions? A still water protected harbor condition. For a ship with machinery amidships floating in a protected harbor, a loading condition that assumes the cargo compartments full and midship tanks empty, and the tanks full and the ship down to her marks is usually adopted. This results in an initial hogging tendency for this type of vessel. For a tank ship or cargo ship with machinery spaces aft floating in protected harbor, the loading condition assumes that cargo tanks or compartments full, at the ends empty. The ship is down to her marks and is adopted and results in initial sagging condition. These are considered as the maximum reasonable loading conditions, although it's possible for a vessel to achieve greater bending moments in some ballast conditions. It is interesting to observe that the advent of fuel oil and double-bottom tanks has made it possible to reduce extreme bending moments that used to prevail on coal-burning ships where the fuel had to be located near the boiler room. A severe sea condition. Suppose a vessel is heading into waves equal in length to the length of the vessel. The length of the wave is normally measured from the wave crest to wave crest. When the crest of the wave is amidships, the ship is supported by buoyancy, as it were, on the crest, and hogging tendency is created. When the crests are at the ends, however, a great deal of support, buoyancy is concentrated at the ends, and sagging tendency results. Now, of course, the greater height of the waves, the greater bending tendencies. The ship designer needs to assume a reasonable shape or profile of the ocean wave. The standard wave is known as a trochoidal wave, where the wave profile is in the form of a trochoid, which is a curve generated by a point or radius of a circle, and the circle rolls on a fixed straight line. The height of the wave is arbitrary, assumed to be equal to 1/20th of the length of the wave. Now, when the vessel with its initial hogging tendency is due to loading suspended on the crest of a trochoidal wave, which creates a hogging tendency, the two effects are added. When this vessel has a crest of the waves at the ends, the sagging tendency due to the wave action counteracts the some extent of the hogging tendency due to the loading, and the result of bending moment is considerably less in this condition. It is apparent then that the critical bending moment for a vessel with machinery space amidships is the hogging condition. This is the condition that the designer considers the maximum reasonable severe condition, and one in which he must base the strength calculations. The reverse is true for a tanker on any ship with a machinery aft. Here the sagging condition is a critical bending condition and the one investigated. The above assumed for the full load condition, it would be wise ship's officer to investigate the most severe condition of the ship in the light draft condition as it is being ballasted, or part loads of cargo being shifted coastwise in the still water and sea condition. Remember what is illustrated in figure 10.1. At the ends of this chapter, recommendations will be reviewed to avoid overloading bulk carriers and structures, which covers preparation of the sequence of cargo and ballast operations to avoid dangerous situations. When a vessel is in a hogging condition, the upper deck undergoes maximum tensile stress. The bottom area, maximum compressive stress. However, as the crest passes to the end of the vessel, the sagging tendency of the vessel will develop, and stresses in the upper and lower flanges of the hull girder will reverse. Therefore, a vessel passes through waves as it is a constantly shifting direction of stresses along the flanges of the hull. Longitudinal shearing stresses are also developed, since the tension and compression vary uniformly from the top of the hull girder to its bottom. Small differences in tension and compression from layer to layer result in shearing forces between the layers. All of this is in conformance with the beam theory of strength. You have seen what constitutes reasonably severe bending moments. This next problem is considered in that calculation, the bending moment and shearing stress, which results from the bending conditions. And that's where we'll resume next week. Thanks for listening. Well, that's my license question of the day. I hope you enjoyed it. I hope it challenged you. And if you have any questions about it, you know where to find me on LinkedIn. Now, please stand by for a word from my sponsor.